How to choose the smoothing parameter. In a nonparametric methods for density estimation or regression, the critical parameter is the smoothing parameter as used in bin width or kernel spread h or the number of neighbors k. The aim is to have an estimate that is less variable than the data points. As we have discussed previously, one source of variability in the data is noise and the other is the variability in the unknown underlying function. We should smooth just enough to get rid of the effect of noise, not less, not more. With too large h or k, many instances contributed to the estimate at a point, and we also smooth the variability due to the function. Over smoothing, with too small h or k, single instances have a large effect. We do not even smooth over the noise under smoothing. In other words, small h or k leads to small bias, but large variance. Larger h or k decreases variance, but increases bias. Germain, Bienenstock, and Doret in 1982 discussed bias and variance for nonparametric estimators. The requirement is explicitly coded in a regularized cost function as used in a smoothing splice. Figure 8.11 kernel estimate for various bin lengths for a two-class problem. Plotted are the conditional densities P of x conditioning on Ci. It seems that the top one over-smoothes and the bottom under-smoothes, but whichever is the best will depend on whether the validation data points are. The summations of r to the t minus g hat of x to the t, then to the square summing for all t, plus lambda of the integrations of g hat double prime of x, then to the square dx, integrating starting from a to b. This is the formula a.22. The first term is the error of fit. The closed interval AB is input range. G hat double prime dot is the curvature of the estimated function G hat dot and as such measures the variability. Thus, the second term penalizes faster varying estimates. Lambda traits of variability and error where, for example, with large lambda, we get smoother estimates. Cross-validation is used to tune hk or lambda. In density estimation, we choose the parameter value that maximizes the likelihood of the validation set. In a supervised setting, trying a set of candidates on the training set, see figure 8.11, we choose the parameter value that minimizes the error on the validation set. Note: k-nearest versus the kernel-based estimation were proposed 50 years ago, but because of the need for large memory and computation, the approach was not popular until recently. And with the advances in parallel processing and with memory and computation getting cheaper, such methods have recently become more widely used. Textbooks on a nonparametric estimation are Silverman 1986 and Scott 1982. Desarrothy 1991 is a collection of many papers on KN and editing condensing rules. AHA 1997 is a collection of a more recent work. The nonparametric methods are very easy to parallelize on a single instruction, multiple data SIMD machine. Each processor stores one training instance in its local memory and in parallel computes the kernel function value for that instance. Stanvier was in 1986. Multiplying with a kernel function can be seen as a convolution, and we can use Fourier transformation to calculate the estimate more efficiently. Silverman, 1986. It has also been shown that spline smoothing is equivalent to kernel smoothing. The more critical factor in nonparametric estimation is the distance metric used. with discrete attributes, we can simply use the Hamming distance, where we just sum up the number of non-matching attributes. More sophisticated distance functions are discussed in Webb, Chirac, Aha, and Mori in 1997 and Webb 1999. In artificial intelligence, the nonparametric approach is called case-based reasoning. The output is found by interpolating from non-similar past cases. This also allows for some knowledge extraction. The given output can be justified by listing these similar past cases. Due to its simplicity, KNN is the most widely used nonparametric classification method and is quite successful in practice in a variety of applications. It has been shown in Cover and Hart 1967, reviewed in Duda, Hart, and Sturck in 2001, that in the large sample case where n goes to infinity, the risk of nearest neighbor k equals to 1 is never worse than twice the Bayes risk, which is the best that can be achieved. And in that respect, it is said that half of the available information in an infinite collection of classified samples is contained in the nearest neighbor. Cover and Hart 967-21. In the case of KNN, it has been shown that the risk asymptotes to the Bayes risk as k goes to infinity. Nonparametric regression is discussed in detail in Hardo 1990. Hasty and Dipshirani 1990 discuss smoothing models and propose additive models where a multivariate function is written as the sum of univariate estimates. Locally weighted regression is discussed in Atkinson, Moore, and Shaw 1997. These models bear much similarity to radial basis functions and mixture of experts that we will discuss in Chapter 12. In the condensed nearest neighbors algorithm, we saw that we can keep only a subset of the training instances, those that are close to the boundary, and we can define the discriminant using them only. This idea bears much similarity to the support vector machines that we will discuss in Chapter 13. There, we will also discuss various kernel functions to measure similarity between instances and how we can choose the best. Writing the prediction as a sum of the combined effects of training instances also analyze Gaussian process in Chapter 14, where a kernel function is called a covariance function.